Hey everyone, and welcome to Dr. Abu RTN Academy channel. Today we are going to discuss part 7 of the descriptive statistics and the biostatistics subject. In the last video, we stopped at box and whiskers plots, or sometimes they are calling Boxplot only, or box and whiskers plots. Okay, so here in this video, we are going to see the 5 numbers summary, or the 5 numbers which we can use to give a conclusion, okay, or to describe a set of data which we have, okay, based on the box plot or box and whiskers plot. As we discussed last time, the first point will be the median, okay, so we should have the median of the data. Then we'll have, if we start at the 0 from here, because last time we took it horizontally, okay, if it is horizontally, so it should be like this. Let me do it nicely. Okay. So here, this is the box, and this is the whiskers which we have. Okay. Then this is called median. And here, this is the start from the left. So this is the lowest value. This is the maximum value, or minimum, here maximum value, okay, or largest value, here the lowest value, okay, and then here this is Q1, the first quartile, and this is the third quartile, okay, so this first quartile, third quartile, and this is in between called interquartile, between the first and the third, interquartile. So, if the box plot is drawn vertically, we have to look at the starting point here. The start is 0 is up or down. 0 usually it is down. So here, this is the minimum value, the smallest value, okay, of the set reading. This is the smallest value. And this is the biggest or the largest or the maximum value, okay? And this is, of course, this one is the median, okay? If we start from the minimum, this is the minimum, so this is Q1, the first quartile, this is the median, this is Q3, and this is the maximum. I hope it's clear. So, if anyone wants to revise what we have studied in the last video, so here we have just the serial number, we put here, this is the serial number. So this is item number 1, item number 2, item number 3, item number 4, and so on up to item number 25. So the total number of the data which we have in the sample is 25 measurements, okay? So we have 25 measurements. So the first thing, as we said last time, we have to put them. So we have to put the data in order. So starting from the first one, 0.6, we arrange them in order. As we say, the first thing, we have to count them, how many. We found that they are starting from 1 up to 25, there are 25 number. So n equals 25. Then the second step, put them in order, arrange them ascendingly or descendingly, it doesn't matter, ascending or descending. So here, starting from 0.6, it goes up, number increasing every time until we reach 6.1, the maximum number, okay? So the minimum number is 0.6 and maximum number is 6.1. So we have n equals 25. 25 is even or odd, it is odd number. So I have to add 1 to it. I cannot divide 25, so I have to add 1 to it. It will be 25 plus 1 divided 2, half of it. So it will be 26 divided 2 equals 13. So item number 13 in the sample will be the median. So item number 13, 1, 2, 3, 4, up to 13 here. So this is the median. So my median is 3.4, okay? Then I consider that this median is not existing. So how many numbers before and how many numbers after? I have the number of measurement before the median 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And also I have 12 after. So this 12, I have to have a new median for this 12 only, for the bottom part or the upper part. And if it is horizontal, for the left side or the right side, okay? So I have 12 number. 12 is even number. Every number I should have 2 median points. So I have to divide by 2 equals 6. So it will be 6 and plus 1, the next one, which is 7. So item 6 and item 7. So item 6 and 7, this would be my median. So the median would be the sum of them divided 2. So 2.3 plus 2.1 divided 2 equals 2.4 divided 2 equals 4.4 divided 2 equals 2.2. Okay, so this will call the first quartile, which is here. Okay, first quartile. The same thing we'll do with the upper half. So upper half also we have 12 numbers. So I have to count 6 and 7 either after the median here, 1, 2, 3, 4, 5, 6 and 7, or count from the top, 1, 2, 3, 4, 5, 6 and 7. So in all cases there will be item number 19 and item number 20. Okay, so item number 19 and 20 are 4.2 and 4.5. So the average of them, in order to get the median for this upper part, it will be 4.5 plus 4.2 divided 2 equal 8.7 divided 2. So half of them will be 4.35. Okay, so now we have got the median, we have got the upper, the first quartile, okay, which is this one, and the third quartile. Okay, so I have to draw the box plot between the first and third. So the first is 2.2 and third is 4.35. So I have to come here at 2.2. So here this is 2, so I come here 2.2 and I draw a line, okay, and I have to go at 4.35, for example here 4.35, and draw it here, and then draw a box. Okay, then I draw whiskers from this box till the end point, the minimum value, the smallest value, which is 0.6 here, and the maximum value 6.1 here. So here 6.1 and here 0.6. Okay, it should be a little bit upper here, above here. So I have to draw line here and I have to draw line up to this one. So this is the box plot or box and whiskers plot as we have taken in the previous video. In this slide, we will talk about the measurements. Measures of spreads. Whether our data is spread out of a long area, long distance, very spread out, or it is very concentrated or focused in a small area. So we can see that some of the data are very, like this data is very closely clustered. All the data, most of the data are together, okay, compared to the other sample. This sample, if you look at it, the data is spread. See, the data spread from here to here, see, over a long distance. See, the data is very spread, but here the data is closely clustered. Okay, so here if you look at the data are closely clustered all together, okay, in a smaller area. But here it is over a very lengthy or very long distance, so it is spread out. Okay, so this is called the dispersion. Dispersion, how far the data are spread out. Okay, so I have the range of the data. So this data, the first one which I have here, this is the range, the starting point. So if I want to say the range of my data, so I have to talk about the starting point and the end point. So starting from, for example, 1 up to 10, so my range is 9. But this data starting from 3 up to 7, so the range is 4. Okay, this is called the range. So the range is the difference between the maximum value and the minimum value. The maximum value in the other graph and the minimum value. So the range is the difference between the smallest and largest value of the set. Okay, and it is useful to give us a range. If the data spread over a wide range, this means that the data is not concentrated, the data doesn't have common trend to go together. It is varied a lot, spread out, okay? I have something else called variance. Variance, this is a measure of dispersion of the data relative to the scatter value, and we'll come to the variance and what is the difference between variance and the standard deviation in the next slide. So coming to the standard deviation and the variance, we need to understand or to distinguish between the variance and the standard deviation and how to understand them. That's why I'll give this example to just help us to digest and understand the difference. Okay, by drawing these numbering lines, okay, this one and this one, I just drew them. Let us assume that we have two sets of data, and in these two sets of data, let's just write them here so we'll not mix them with the other stuff which we have here, okay? So the two sets of data will be, let's assume 3, 5, and 7, and the other set will be 4, 5, and 6. If we want to get the mean or the average of the first set, this is the first set, and this second set, the mean or the average, so here x bar for the first one and x bar for the second one. So x bar for the first one would be the sum of them, 3 plus 5 equals 10 equals 8 plus 7 equals 15 divided 3 equals 5. The second one, 4 plus 9 equals 9. 4 plus 5 equals 9 plus 6 equals 15. So 15 divided 3 also equals 5. So the mean for both of them is 5. So what this 5 gives us as an impression? We can know that the average of both of them is 5. But does all of them are closer to each other? All the numbers are closer to each other, or they are far away or spread out from each other? So this spread out of the data from the mean, it will not be clear, or we cannot get it from the mean. So we have to look at other way how to see how far the data are spread out from their mean. So if we represent this, the first set on this numbering line here, let us represent them. So here I put 3, the first number, okay, then 5, then 7. This is the mean. Our mean is 5. We just got it now, okay? So this data is very far. The 7 is very far from 5, and 3 also is very far, so that is spread out. Look at the other set, the second set, which we have here. So we have here, let's use different colors. We have 4, we have 5, and we have 6. So this is the mean. This was the mean for the second set, okay? This is mean for the second set. So the data here, they are closer to each other. See, the data here are closer to each other. So when we got the average or the mean only, we got the average for both of them for the two sets is 5. So the average here, if we rely on it only, it will mislead us. We'll get a wrong message, wrong impression that both are the same. But here, once we come to know the spread out of the data, we got a new idea or a new area, new dimension to think out of the average or the mean concept, which is the spread out. So both of them has the same average, but both of them are not the same. Here the data are spread out very far from the mean, okay? So the difference between them and the mean is very big, okay? This is called the difference or the variance between them and the mean, okay? So here the 7 is very far from the mean. So the mean, which is x bar, so if I say 7 minus x bar equals 7 minus 5 equals 2. Okay, the same thing here also, 3 minus x bar, which is 3 minus 5 equals minus 2. Okay, this is for the first set. For the second set, it will be 4 minus x bar, this first x bar and this second x bar, equal 4 minus 5 equals minus 1. And the second one will be 6 minus x bar, x2 bar, which will be 6 minus 4 equals 1. 6 minus 5, 6 minus 5, 6 minus 5 equals 1. So here just let us clear this one. Okay, equals minus 1 and equals 1. So here 1 and minus 1, and here 2 and minus 2. Okay, so we can see that the data are deviating or spreading out away from the mean by 2 and here by 1. Okay, so this is called the variance, but it's not exactly the variance, but this is the gap between them. So the data here is more spread out than the data in the second set. So from here the idea came that we should not rely only on the average or on the mean of the data. We have to look how the data are spread out. Are all the data compacted or closely clustered closer to each other, or they are spread out? Okay, so from here the idea came that we have to see how far are the data from the, if we assume this is the midline, so some data are here closer, but maybe in other sample the data will be very far. Okay, so this data in this sample, they are far from the mean than this data in this sample. Okay, so this is another idea how the data are spread around their mean or around their average. So if we also looked at this example here, we have two sets of data also, set 1 and set 2. The set 1, if we try to get the mean of the data, or x bar, could be x bar 1 and x bar 2, just to distinguish them. Okay, so the first one, it will be the sum, 28 plus 29 plus 30 plus 31 plus 32. The total is 150. How many they are? The count 1, 2, 3, 4. 1, 2, 3, 4, 5. So total 5. So the mean or x bar or the average is 30. The same thing here, 10, 20, 30, 40, 50. So total is 150 divided 1, 2, 3, 4, 5 divided 5 equal 30. So the mean or the average for both of them are the same. But the data are spread out in the second, if we can see here, it's 10, 20, 30, 40, 50. So the data are very spread. The gap between each one is 10, 10, 10. The data that are spread out far away. But here they are closer. So if we look at the mean here, the mean is 30, but all of them are like one family, very closer family, okay, or closely clustered family. So here 30, and then the other items are 29, 28, very close to 30. After 30, 1 second. Okay, so after 30 also the same thing here, 30, 40, 50. So here 30, 31, 32, very close. And before that 29, 28, all of them 28, 29, 30, 31, 32, very close to each other. But here 30, after that 40 and 50, tens, the gap is 10. And here 20 and 10, the gap is very big. So this data set is more spread than the first data set which we have. Okay, that's why the average is not enough to compare or to summarize or to get a conclusion of the data. And that's why we came to an idea. We have to check the difference between each number here and the mean, each number and the mean, okay? And then we square them, okay? And we'll see in the next example how we can square them and how we can get the variance. So the variance here, they call the population variance or the sample variance. Variance means that x, each number, like 28, like 31, like 32, minus the mean or the average, okay, minus x bar. And then this difference, we have to square it. And after we get for x1, for x2, for x3, for x4, they will have to sum them, then divided by n. This is in case if we are talking about the population. We'll come also back to the difference between the variance for population and the variance for sample. So if we look at this example, in this example we have x are getting this set of data. So x is equal 7, the set of data 6, 7, 8, 9, and 10. 5 elements in the set of data, okay? So how to get the standard deviation or the variance We'll come to know the details of this, but just I want to teach you the way how to get them, because actually it is confusing if you keep minusing or getting the variance or the difference between every item and the mean and then score them. So if you tabulate them or put them in a table, it will be more easier. So just I put x, okay, in a table in one column, okay, and I list all of them down. I get set and put x here, 7, 8, 9, and 10. So now I have listed them down, 6, 7, 8, 9, 10. Then I have to get x bar. X bar, it's outside the table. So I have to 6 plus 7 plus 8 plus 9 plus 10. So here, divided how many they are? 1, 2, 3, 4, 5, divided 5. Okay. So it equals 40 divided 5. 5 equals 8. So this is my mean or average. So I write x bar and 8, okay, against each one. 8, 8, 8, 8, okay? Then the third column will be x minus x bar. So this is the gap or the difference between each one. For example, you remember the previous example, I said this is the mean. For example, the mean is 8, okay? And I have here 9. So the difference between the item, the x, and the mean. If it is 6, the difference between 6 and the mean as well, okay? So this is the gap or the difference between them. So I have here each x minus x bar, not x bar minus x, or one time x minus x bar and other time x minus x bar. No, always we have to keep x minus x bar, whether positive or negative. So x minus x bar, 6 minus 8 equals minus 2, 7 minus 8 equals minus 1, 8 minus 8 equals 0, 9 minus 8 equals 1, 10 minus 8 equals 2. If you look, because this is just a sample, okay, x minus x bar, they adds up to 0. So here minus 2, minus 1, minus 3, plus 1, plus 2. So the sum of them is 0, okay. That's why the idea came here that, okay, we have to square them up. So the law which we have, so the first thing we have to get to write down, to list down x, okay, then to put x bar, and then to get the variance or the difference between x and x bar, x minus x bar, x minus x bar, and then this column has to be squared in the next column, okay. So it is a very systematic way, okay. Just list down x, okay, the values of x, then calculate x bar, which we have here, x minus x bar, okay, put it here, this is a column. Then the second column, so first column x, second column x bar, third, first minus second. So the first column minus x bar. Then the first column would be the same column but squared, okay, x minus x bar squared. So here minus 2 squared, it will be 4, because anything squared, whether positive or negative, it will be positive. The answer will be positive. So minus 2 squared, 4. Minus 1 squared, 1. 0, 0. 1, 1. 2, 4. Then I have here the sum. I have to put the sum of all of them. So the sum will be 10. Okay, 4 plus 1 equals 5, plus 0 plus 1 plus 4 equals 10. Okay, so this is x minus x bar squared together. Okay, the formula here, it says that sum of x minus x bar square, which we already got it here. So we got directly by having this column and having the sum of it, we'll get the denominator as it is. Okay, so it will be x minus x bar square. This is the numerator. Then the denominator will be n minus 1 and put under square root. Then we'll get the standard deviation. We'll get the standard deviation. This is the formula of the standard deviation, but for sample. If I have a sample, this is for sample. If I have a population, it will be slightly different, and we'll come to it in the next example. So in this example, we'll see that we have two sets of data. The first set of data, if you remember the previous example which we have taken, 28, 29, 30, 31, 32, which are very closer to each other. And we have also the other example, which is 10, 20, 30, 40, 50. And we said that the mean or the average for both of them is 30. So both of them are having the same average. But if I follow the same way of calculating the standard deviation or the variance, okay, forget about the difference between the variance and the standard deviation. I'm going to tell you, but after having this few examples, I'll tell you the difference between variance and the variance and standard deviation, and the difference between sample and population with respect to these calculations. Okay, so I'll put the first one. I'll deal with each sample separately. So the first sample or the first set of data. Okay, I'll take it first. Okay, so I'll take 28, put it here, 29, 30, 31, and this one, okay, 32. Okay, so the first column is x, the value of x, okay? The second column, as we said, x bar, okay? We'll put x bar, it should be, x bar is 30, so I put here 30, 30, 30, 30, and 30. So the third column will be x minus x bar or x minus u. We'll come to know the difference between mu and u and x bar. Okay? But for time being, consider them the same. They are the same actually, but mu is used, is the mean of the population. Okay? It is the mean or the average of the population. Okay? And x bar is the average or the mean of the sample. That's it. The only difference between them, that mu is the mean for the population, and x is the mean for the sample. So the only difference between the mean, the mu, and the x bar, mu is the mean of the population, and the x bar is the mean of the sample. Okay, so we can put here mu or x bar. It doesn't matter, but you have to make sure that you are using sample or population. Okay. In this example, we are talking about the population. That's why you will find here some changes or some difference from the previous example. You will find that the S square, it changed to sigma square. Because in case of sample, we'll come to this comparison actually. In case of sample, we're calling it sigma square. Sample, we're calling it S square. Population, we call it sigma square. For the case of sample, we're calling it x bar. For the population, we're calling it mu. Okay? For the sample, we have in the denominator n minus 1. But for the population, we have in the denominator n capital. Okay? These are the difference, and we'll come to all of them. But forget about them for the time being, because it's not required in this example. Just because you may see some different notations here and there. Okay, so here the first column we just put in the x, okay, the values of x, and second column will have x bar, okay, or mu. You can call it here. Now you know the mu, so we can call it mu now. Because mu is x bar, but because we are talking in this example about the population, so we can use mu. Mu is x bar, okay, or x bar. So the third column will be x minus x bar or x minus mu, okay, x minus mu. The fourth column will be so the first column x, second column x bar. The third column will this minus this, x minus x bar. This is the column. The fourth column will be the last column, third column, but a square, okay. So x minus x bar, x minus mu or x bar square, and then we'll have the sum. The sum here will be 10, okay. So the sum of x minus mu or minus x bar is 10. Then we'll write the formula, okay, sum of x minus mu square or x minus x bar square, denominator, which we said this is the figure. Okay, so this is the figure for the denominator. So we'll say denominator equals 10, sum of x minus x bar square or x minus mu square divided n, okay, and we'll write it. So in order just to avoid confusion here, we'll write it, we'll use the proper one. So x minus mu square divided n capital. This is the variance, okay. This is the variance, we call it sigma square, okay. So here equals 2. So the variance in the first set of data was 2. The variance was 2 because the numbers are very close to each other. Let us do the same thing for the second example, which is 10, 20, 30, 40, 50, and so on, and their mean or average is the same. Let us see how is their variance, how they are varying from the mean, okay? So sigma in the previous example was, sigma square was 2 in the previous example. Okay, it was 2. In this example, if we take the second set, we put 10, 20, 30, 40, and so on. So this is the first one, the first column, okay? Second column will be also mu or x bar, which is 30, okay? 30, 30, 30, 30. So we have 10 minus 30 equal minus 20, 20 minus 30 equal minus 10, 30 minus 30 equals 0, 40 minus 30 equals 10, 50 minus 30 equals 20. So here x minus mu, then the fourth column will square them, okay? Every item square, 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 okay? Then we'll get the total of them. The total is 1000 here. And how many they are? So the formula, sum of x minus mu squared divided n capital, okay? N capital is 5. So the variance, which is sigma square, is 200. See, imagine here it is 2 and here it is 200. So if the sigma square is 200, means that the data is very spread out. But when it was 2, it was only 20, 28, 29. But here there is one point which always confusing and the students are missing it out. They think that the difference is 2, like the difference between the number. The difference here, the spread out, the difference in numbers is, even if we take the biggest number and the smallest number here in the second set, the biggest number or the maximum number is 50 and the minimum number is 10. So the difference or the range is 40. So how we can get 200? Okay, here, okay, it could be acceptable because we have the maximum 32 and the minimum is 28. So the range is 4. So it could be accepted that it is 2. But here it is even, the variance here is more than the difference between the maximum and the minimum, between the range. Actually, there is something which you have to keep always in mind. Otherwise, you'll do a mistake when you summarize or explain or describe or interpret the data which you have. That the variance which you have got here, it is not sigma, it is sigma square. Okay, so still if you want to get sigma, you have to have the square root of it. So square root of 2 equals 1.14. 1.4. Let me calculate it. So it equals 1.41. Okay, so this is the sigma. This is the deviation which we have. And here, if we took the square root of 200, which is almost will be 14.1 or 14.15. Okay, so this is the spread out. This is the sigma. Sigma will come to know now how we can represent the sigma in the normal distribution and how it impacting the normal distribution graph, or how it looks like, and whether it is closely clustered or it is spread out. So this we are going to do. But for time being, we want to say here that, see, because the gap between the numbers are very big, their variance, population variance or sample variance is very big. And the same thing is applicable to the standard deviation. So standard deviation also will be big. So sigma could be standard deviation or could be the variance. But variance is always sigma square or S square. If you are talking about the sample, it will be S square. If you are talking about the population, it will be sigma square. This is for the variance. So variance always square. But standard deviation, it is S or sigma only, not square. This is the standard deviation. But variance, it is sigma square, S square, or sigma square. Okay, just keep in mind. I remind you in the next slide about it. So in this slide, we are going to see the variance and the standard deviation, the difference, or just a quick comparison between the variance. Let me just change the color. Okay. The difference between the variance and the standard deviation, okay? The variance, as we said, if we are talking about the sample, we'll call it S square. Population, we call it sigma square, okay? This is the standard deviation. This is SD, standard deviation, okay? If we are talking about the variance, let us write the other way around, because here standard deviation on the right side and variance on the other side. So here in the case of the variance, okay, so variance always is square. We're talking about the square. In the case of sample, we're called S square, okay, and in the case of population, we're calling it sigma square. Okay, so variance always square. The standard deviation is just the square root of them. Square root of x is square, it will be s. So this will be the standard deviation. So standard deviation is the square root of the variance. In the case of sample, it will be s only. In the case of population, it will be sigma only. Okay, so since the variance always square, so it will be always positive, because you cannot have square, anything squared, you cannot have it negative. So variance always is square, and standard deviation could be negative and it could be positive. You have a sample, for example here, you have the mean, or so one point will be in this side and 1 point in the other side, okay? But for the variance, it will show you how far the distance from the mean, okay? Is it here or here or here? But it is one side, because all of them will be positive, how far they are, okay? But in the case of standard deviation, it can show you both sides, positive and negative. So coming to this comparison, which we have, the variance is a statistical measure on how far the numbers are spread, because this is square, how far they are spread in the data set from their average, okay? But for the standard deviation, the dispersion of the values in a given data set relative to their mean, okay? In comparison to their mean, how they are spreading, okay? The variance, it helps to determine the size of the data spread. But the standard deviation, it measures the absolute variability of the dispersion. Okay? The two most and famous differences between them actually is this one and this one. So, for variance, it is calculated by taking the average of the square deviations. Okay? If you remember, we have taken x minus x bar. Here he's calling it m. It is x bar or m. It doesn't matter, or mu. Okay? X minus x bar square divided n. Okay? Divided n. So it is calculated by taking the average of, average means anything difference divided the total number divided n. This is the average. Something that sum divided n. So here also we have the sum, but this sum is not sum of x. It's not sum x divided n. No, it is sum of x minus x bar square. So the sum of the squares, okay? So here, the sum of x minus x bar square. So it's called the sum of the square deviation. This is the deviation. Deviation means something deviating from another. So x minus x bar, this is the deviation of x minus x bar, deviation. And then x1 minus x bar, x2 minus x bar, x3 minus x bar. Then all of them are squared, okay? So it is calculated by taking the average of the square deviation. This is square deviation, and if I divide it by n, it will be the average. Anything divided by the count of them, it will be the average. Okay, so it's calculated by taking the average of the square deviation, here of each value of the set. Okay, but in the case of standard deviation, it is calculated by taking the square root. So after I get the deviation of the averages, okay, x minus x bar, this is the deviation squared. I have to take the square root of all of them by taking the square root of the variance. So I have to get the variance and again the square root of the variance. That's why the variance is same as standard deviation, but it is just squared. Okay. I will not spend a lot of time on this slide or this example because it is out of the course, but just for clarity, what is the difference between them? As I just mentioned, that in case of the population, we are using the symbol sigma. Okay, if it is variance, so it will be sigma square. If it is population and the standard deviation, so it will be S only. If it is sample, and the variance, it will be S square. So sample always take S. Sample takes the symbol or the notation S. Population take the notation sigma. If it is variance, it will be square. If it is sample and the variance, it will be S and square. Okay, so S for sample, variance always square. Standard deviation, it will be for a sample, it will be S. Standard deviation for population, it will be S sigma square. This is standard deviation for population. Okay, so anything for population, it will be sigma. Okay, and if it is standard deviation, it will be without a square. Sorry, here, okay, sorry, this is sigma only, not sigma square. So standard deviation for population, it is sigma. Standard deviation for population is sigma. Okay, standard deviation for sample, it is S. Okay, so any standard deviation doesn't have a square. It will be either sigma or S. If it is for population, it will be sigma. If it is for sample, it will be S. But for variance, sample for variance, it will be S square. Population for variance, it will be sigma square. And in all the cases, it is X minus the mean, the average or the mean. In the case of the population, the mean is called the mu, not X bar. In the case of sample, mu is called X. The only difference which is confusing is N. If he told me in the problem it is a sample, so I have to use N minus 1. This is the most important point. Okay, if he told me it is a sample and I'm using the sample S, okay, or S square, so S in case of standard deviation or S square in case of variance, I have to use N minus 1. All the sample, N minus 1, okay, in the denominator. All the population, if he told me in the problem it is a population, so I have to use N only, capital N, everyone writing capital N. Mu and X bar, they are the same, but this is the mean of the population and this is the mean of the sample, okay? But N is the total number of the population in capital, and N minus 1, it's used only if he told me it is a sample, okay? So when we talk about the standard deviation, we have to come to know about the standard deviation for a sample, and we have a rule called 68, 95, 99. So this is the rule of 68, 95, and 99. This is called a famous rule called 68, 95, and then 99. So standard deviation has fixed rules. He said that if I have deviation of 1 sigma from each side, so if I move here, this is my axis or my mean, okay, this is the mean value which I'm calculating, the mean value. If I deviate from it by 1 sigma, which I don't know, sigma differs from one sample to another sample, I have to calculate it. So this is the concept of sigma. So sigma, if I moved it 1 sigma this side and 1 sigma on the other side, so this range should represent around 68% of the total sample, okay? So 2 sigma, 1 sigma from this side and 1 sigma from the other side should represent 68%, okay? If I moved, instead of 1 sigma from this side and 1 sigma from the other side, so here 1 sigma here and 1 sigma here, we call it 0 plus 1 sigma minus 1 sigma, plus 2 sigma minus 2 sigma, plus 3 sigma minus 3 sigma. So if I moved 1 sigma from each side, the percentage of this 1 sigma represents 68. If I move 2 sigma, I should have 95% of my data represented here. So how can I guarantee that if within this area only, the sigma guarantees that if you moved 1 sigma from here and 1 sigma from there, it will be 68%. If you move 2 sigma from here and this 2 sigma from this side, it will be 95%. If you move 3 sigma from here and 3 sigma from the other side, it will not be 100%, it will be 99. And some people say 99.7 even, but it will be very close to 100%. It will be 99, the 3 sigma will be 99. So 99.7 or 99% of the data is represented by 3 sigma from each side. 3 sigma from here and the 3 sigma from here. So overall 6 sigma. 3 sigma from here and 3 sigma from this side. 95% of the data, which is a good accuracy, very good accuracy level, can be obtained by moving only 2 sigma from each side. Okay, by moving 2 sigma from each side, we can have 95% of the data. The formula which we have taken, which is sum x minus x bar square divided is in the case of sample n minus 1. Okay, this formula guarantees that the value which will arrive to for sigma, the value of the sigma or the value of s which you arrive to, okay, the standard deviation, the value of s, because we have to calculate it. This calculation guaranteed that if we move this value of s 2 or 11 or 15 or 5 or whatever the number of s which you will have, it guarantees that this number will have 68%. If we move one sigma from here and one sigma from here. And this 2 of this number from this side and 2 from this number from the other side guarantees that we'll have 95%. 3 of this number from this side and 3 from the other side, it will guarantee also that I have 99.7%. In order to guarantee that there is no confusion in the data, so one sigma, one standard deviation from this side, and one standard deviation from this side of the 0, and one standard deviation from here, okay, represents 68.2 or 68%. So it is 34% from this side. So each sigma represents 34%. But keep in mind that this distance is not 1 sigma, it is 2 sigma. 1 sigma from this side and 1 sigma standard deviation from this side. So 1 standard deviation from here and 1 standard deviation from this side, okay? So 2 standard deviations represent 68. So 1 standard deviation from this side represents 34%, and the other standard deviation from the other side will represent 34%, okay? So if we add it to this, we have 95%. It represents by 2 sigma, which is here, okay? So we have the overall here is 90, let me highlight it to you, 95%.4, okay, is represented by 2 sigma, okay? So if I split into 2, so I have to add here more 13.6% to the 34, okay? So it will be 47.8. So 47.8 from here, 47.8 total. But because I have here 34.1, he added here 13.6. Anyway, so the overall will be 95, okay, 0.4 for 2 sigma, and you can divide it by 2 on the calculator, okay? By the way, for the calculator, I'll give a separate video how to calculate the standard deviation, the median, the mean, all these things from we're using the calculator in a separate video after this one, okay? So if I'm looking at the percentage of the data, which is 95% or 99%, 99 I can take 3 sigma from each side, okay? 95% I can take 2 sigma only from each side. If I'm looking only for 68% of the sample, of the readings, of the measurement, I can take only 1 sigma from each side, okay? As we just mentioned in the previous video, we have to calculate the standard deviation, okay, and standard deviation, the percentage is constant. If I have 1 standard deviation from each side, okay, it will represent 68%. 2 standard deviation, it will represent 95%, and so on, okay? So if I have graph like this, so if I look at the green one, see the green one, all the data around the mean, see that this is the mean value, all the data are very closely clustered around the mean, okay? All the data are very closely clustered around the mean here. If I looked at the second graph, which is the red color, so the red color here, it is spread out more than the green one. See, this is the mean, and the data scattered here, spread out for a long distance. But the other one, the green one, it was very close. If I have the mean, so it was very close to the mean, to the average. The data are very congested, okay, or the data are very closely clustered. But in the second case, it was widely spread. In some other cases, it will be more and more spread out. It could be like this. Okay, so this is very spread. This one is closely clustered. Okay, this one is called closely clustered. Okay, closely clustered. Okay. So again, look at the three graphs and let us compare them. So the green graph here, if I took the average or the mean here, okay, and took one standard deviation from one standard or one standard from each side, it will be very small. So here the standard deviation is very small. And also we can notice here that the green color, see, the standard deviation is 0.2. For the red color one, the standard deviation is very big. See, the standard deviation is very big. It is 0.5 or more than double. Okay. For the brown one, for the brown color, let me delete this one so you can see it, the picture clear. Okay. For this brown one, if you take the average or the mean from here, the standard deviation is very big. Okay. 3 sigma from this side and 3 sigma from this is very big. Compared to this green sheet, the 3 sigma here and the 3 sigma here is very small. In the red one, it is a little bigger, but in between. For the brown one, it is very big. So that's why it is 1. So as far as the standard deviation value is big or great number, so this means the data are spread out. Okay, data are scattered and spread out. Okay. Okay, sorry the video gets longer, but I want to finish in one video. So here for the sample, I'm using the simple S. Okay. If I'm talking about the variance, I have to use a square. Variance is a square. Variance sigma square. Okay. So S for sample. Again, S for sample. Sigma for population. Okay. Square for variance. If we have the square root, it will be for the standard deviation. So this is sample, it will be S. Variance, it will be square. Okay. So here equals x minus x bar, because sample we are using x bar. X minus x bar square. We have the column. You remember the first column? We said x minus x bar and then x minus x bar square. Okay, and we'll get the sum of it. This is the sum of it, denominator. Okay. So again, sum of x minus x bar square divided n minus 1. Why n minus 1? Because it is a sample. If it is sample, it will be n minus 1. Okay, for a population, we are not calling it S. It is variance also, so it is a square. But for the population, we are calling it sigma. Or instead of S, sigma square. X minus x bar. Here, x bar we are called mu. Because it is a population, we are called the mean of the population mu. Okay? So it is mu x minus mu square divided n. This is the difference. If the problem, he said it is sample, I have to use n minus 1. Okay, I have to use n minus 1. If he said it is a population, I have to use n only. Be careful of this too. If he said population, it will be n. If he said sample, it will be n minus 1. Okay, so here sample. In this example, he said sample, so I have to use n minus 1. Okay, so he said sample. The first thing, I have to get the mean of them. Okay, so I have 1, 4, 7, and 8. 1, 4, 7, and 8. The mean 1 plus 4 plus 7 plus 8 equals divided 4. The number of them 1, 2, 3, 4. Okay, so they equals 20 plus divided 4 equals 5. So this is the mean. So my mean or average is 5. Okay, so every number here I can put them in a table here. Okay, I can say x equals 1, 4, 7, 8. This is x bar. I put it here, which is equals 5. 5, 5, 5, 5, 5. Okay, then x minus x bar, then x minus x bar square, and you get the total. So here he did it manually. The first item, x minus x bar, 1 minus 5 square, 4 minus 5 square, 7 minus 5 square, 8 minus 5 square. divided n minus 1, and he got the variance of the sample. This is variance of sample. How I know it is a sample? Because it is minus 1. How I know it is variance? Because it is square. Be careful, this 10 is not the number. The biggest number and the smallest number here, the biggest number is 8 and the smallest number is of 1. We cannot have a variance of 10. The difference between them are 7. The gap is 7. How would come 10? Because this is square. I have to get the square root of it, which will be 3 point something. Okay, so this is s square. Have to be careful. It is s square, not s. Okay. Some people ask why here n in the population and in the sample it is n minus 1. There is something called the degree of freedom. It doesn't matter in this topic, but it is called degree of freedom. And the derivation of this formula, actually, it depends on this degree of freedom. So for the sample, the degree of freedom is not n. For the sample, the degree of freedom is n minus 1. That's why they change it to n minus 1 in the case of sample. In the case of sample, either it is variance or standard deviation, it's n minus 1. Okay, the degree of freedom. And here also in the standard deviation is same as the variance, but just a square root. Okay, if you clean this one, you will see the two formulas are the same. See, the two formulas are the same, except we have there's the square root here and the square root there. The square root here will cancel the square, so it will be, instead of variance, it will be standard deviation. And the square root here, so all the variance under the square root. Some people even they used to calculate the variance and then put it under the square root as it is. So you can take the variance in the previous example here. If you see, this is the variance which we had, which is 10 here. This is the variance which we had. Okay, this is square. I can just put it under the square root. So square root of 10, I get the standard deviation directly. Square root of 10, because I need just the square root of this one. Okay, to obtain this. So to obtain the measure of dispersion of the original units, we take the square root. So here we don't have the square root. Okay, so we get the dispersion but not of the original unit, because here it is a square. I told you we don't have 10. I have the range of between 1 and 8 in the numbers. I cannot have 10, but 10 is not the realistic unit. This is unit square, meter square, centimeter square, temperature square, whatever the unit here is square. So in order to get it in the same unit and compare it with this data, I have to get the square root. That's why they said, okay, it's better to have the standard deviation. So to get the depression in the original units, we have to use the square root of the variance. Okay, the square root of the variance, which is called the standard deviation. So standard deviation is nothing but the square root of the variance. Okay, both of them are measuring the depression, how is the spread out of the data, but standard deviation is the square root of the variance. So in the same way we have explained, also here there is an example on the standard deviation of the woman height. So just list down the x, put them x, i, x1, x2, x3, i1, i2, i3, i4. So x is mean x1, x2, x3, x4, x5, x6, and so on. So we list them down. Then we got the mean. So the sum of these divided 14, the number. Okay, so we get the mean, which is 63.4. Okay, so I put the mean here, 63.4 everywhere. Okay, then I have x minus x bar, this column, or every data in this column minus every data in this column, this minus this, x minus x bar. Then this other column, it will be x minus x bar square. I'll get the sum of them. This is the denominator which I am going to put in the standard deviation. So it is sum x minus x bar square divided n, if it is population, or n minus 1 if it is sample. Since it is mentioned here s, so it is a sample, s squared, sample, variance, s, standard deviation. So first thing, I get the sample. If I get this calculation, it will be s squared. Then I get the square of s squared, which is s. So here this square will be 6.55. I get the square root of 6.55. I get 2.56. And there's a note here that you have to use the calculator, which I'm going to give in the next video, which will be a separate video for how to use the calculator to calculate the standard deviation. But you have to understand the concept. So in this slide, we are going to discuss the measure of the spread in the standard deviation. We have already discussed this one, just the definition. Here, in most of the slides and the PDF file, they are talking about the sample, not the population. So most of the time you'll find them using n-1. So it's 90% or more than 90%. The question which will come to you is talk about sample. It's not population standard deviation, okay? Unless it is specifically mentioned in the problem, it is a population for the standard deviation. But 95% it will come as sample, because all the explanation here in the PDF file is on the samples, okay? So here the standard deviation S, even they did not use S and the sigma, S only. So this means all the talk about the sample only is used to describe the variation around the mean, okay, of the sample, of course, okay? The variation, so standard deviation, how they are varying around the mean. This is the mean, how they are varying. Very close, it's the first point, vary by this distance. This one is vary by this distance. This one very far, a little far, little far, little far, and so on from the other side, okay? So this is the mean, and this is one standard deviation from here, from this side, okay? Okay, this is the mean and or the average, and this is one standard deviation. So here in this area we should have 68%. We should have 68% of the data. Okay, one standard deviation, and this is the formula of the standard deviation, which is the square root of the s square, the variance, 1 minus n divided x minus x bar square. Okay, the sum of them. So here also we have one slide about the box plots. Okay, if you recall, we have already studied the box plots, so we have one slide on it. Okay, and just reminding us about the errors and the sum, anything which is irregular or uncommon on the box plots. Okay, so here it talks about the box plot and skewed data. You remember we said skewed data, if we have data like the histogram like this, and then we have small histograms, so it's like a tail. Okay, we say skewed like a tail. The tail to the right, so it's called skewed to the right. If the tail to the left, we call it skewed to the left. If the data are here, so this is called skewed to the left. Okay, and this is skewed data to the right and to the left. We have already studied in the previous slides and the previous videos, in the previous videos for the histograms. But in this, we're going to discuss it also for the box plots. Okay. For the box plots and the whiskers, if we look here, we'll find that this is the box plots and this is the whiskers. We'll find the whisker is very long in one side than the other one. It is not balanced, okay? If it is not balanced, we see that it is skewed. Skewed means has a tail. Has a tail to which side? To the right. So this is called skewed right. Here the tail, the long tail, okay, to the left. So skewed left, because this one is short, okay? If you want to understand it and to digest it fully, if we draw here the histogram, we said that, see, the mean of the data is, it should be in the middle here, but it is not in the middle. It went to the left. This means that I have the big blocks are here to the left. That's why the mean comes here. So, and here the small blocks are here. So it is skewed to the right, okay? Because the long tail to the right, and at the same time the mean to the left. So always in this box plot and whisker, if the mean to the left, so it will be skewed to the right, skewed right, okay? Because this means that most of the blocks are here to the left, because the mean we should have the median, not the mean, the median we should have the data, because the median means that the number of data on the left equal to the number of data on the right. But here it is a small area, okay, small, and the median is here. So this means that the block or the most of the data are all together in this side, okay? That's why all the blocks are here and the small numbers of data are here on the right side. That's why it's called skewed to the right. Skewed to the right means the tail to the right, or you can look at the median here. The median is to the left, okay? So median to the left means the other way, okay? Means skewed, sorry, let me just, skewed right, and the other way around. If the tail is here to the left, the skewed to the left. The word skewed means the tail, okay? But also you can make sure that the median is, if the tail to the left, it's skewed to left, okay? But also the median to the right, okay? Just to make sure. Here it gives you an example. This is one of the symmetry or balance, because you can see here in this one, the median is in the middle, exactly, almost. And here, this whiskers, the hair, which is here, the small line, the whiskers are almost the same thing. So it's called balanced or symmetry, okay? But this one called skewed, okay? Skewed, this means the median is not in the middle, okay? The median here to down, okay? So it is skewed up, the tail up, okay? So here Boxplot remains true to the data and depict clearly symmetry or skew. So it can work for the two cases. So the Boxplot can work for the cases of symmetry and still represent the data, and it can work also for the case of skewed data to the right or to the left, to bottom or up, and still presenting them, okay? And in order to remind you about the right skewed or left skewed or symmetry of the data, he has given here two examples. This one, see, this like symmetry one, like this one, okay? And he has also skewed one, which is this one, okay? So this one is skewed to the right because the tail to the right. I hope this one is clear as well. The last slide in this video is this suspected outliers. Outliers means something which is odd, which is strange, something wrong, maybe an error, something which I suspect that I can catch it. There is an error, there is a mistake here, something which is not in line with others, okay? So outliers are troublesome data points, okay? So are trouble points. Their reading or their location or their place is not, it looks like they are consistent or coherent to the other data. It looks like they are anomalous, they are odd, okay? And it is important to be able to identify them so we can take them out. So how I can identify them? If you remember, we said in this, okay, we have here the median, for example. In this box plot, we said that we have the first quartile, Q1, we have here Q3, and the difference between Q1 and the Q3 is called interquartile, okay? And then we have here Q4, and of course we have here Q1, so here 0, okay? 0, here Q1, and here Q3, and of course here Q, the median is Q2, okay? So the difference between Q1 and the Q3 always called the interquartile. So interquartile is this box, okay? The difference between Q1 and the Q3, always. The difference between Q1 and the Q3 is called interquartile. Q1, Q3, and this Q4, okay? And this is 0, and the median is Q2. But what I'm care of is only the difference between Q1 and the Q3. This is called interquartile. If this is 6 and this is 18, so the interquartile is 12. 18 minus 6, 12. Okay? So if I want to identify anything which is odd or outlier, okay, I have to check the interquartile. It's called IQR, interquartile. IQR, interquartile, the difference between Q1 and the Q3. Or Q3 minus Q1, okay? It's called IQR, interquartile. If I check the difference between Q3 and the Q1, the interquartile, and I find I have a number which is 1.5 times, 1.5 times of the interquartile distance, or length or measurement, this means it is outlier. Okay, so let us read the slide. So the outlier are troublesome data points, okay, and that's important that we are able to identify them. One way is to raise a flag, okay, for a suspected outlier. If we find it, we have to identify it. We should not entertain or accept it because it may be a mistake or an error in our experiment, okay. That for a suspected outlier, to compare the distance from the suspicious data, the wrong data, or the data which I'm not happy of it. I don't feel comfortable. They call suspicious. The suspicious data, okay, point to the nearest quartile. So I have to measure the data, point to the nearest quartile, to Q1 or to Q3. So I have it here, okay. For example, this is 0, this is Q1, this is Q3. Okay, and I have data here. This data I feel it is wrong or outlier. So I measure the data between this point and the nearest quartile, which is Q3. Okay, or the data is here, I measure it to Q1, to the nearest quartile. If this distance is more than, could be 10 numbers, not only, it could be 10 data or 5 data or 3 data, not only 1 point, it could be 10 points, all of them. If they are more than 1.5 of this length, the difference between Q1 and the Q3, okay, this means that this data is called outlier data or suspected outlier data. So here, let us just read it. One way to raise the flag for a suspected outlier is to compare the distance from the suspicious data point, okay, to the nearest quartile, which is Q1 or Q3, and then compare the distance to the interquartile range. The distance, which I found here, the distance, for example, let us have a smaller one. So this is Q4 and this Q3. This is Q1, okay. This is 0. So I have a point here and another point here, for example. Okay, so I have to measure the distance between this point, which I'm suspecting it is an error or outlier, or these points could be many points, okay. One of them, I measure the distance to the nearest quartile. So for example, for 24, okay, 24, and this one is 6, and this one is 18, okay, interquartile 1 and quartile 1 and the quartile 2, 6 and 18. So the distance between quartile 1 and the quartile 3 is 12, and this distance is 24, which is 2 times of the distance. So this means the data here is suspected outlier. When then compare the distance of the interquartile range, distance between L1 and L3, okay, we call the observation suspected outlier. When we can call it suspected outlier, it has a problem, or suspected outlier, if it falls more than 1.5 times the size of the interquartile. If the size of the interquartile, as I said just now, is 12 between Q1 and the Q3, and this distance is 24, so it's more than 1.5. So it's called, this point will call suspected outlier. Okay, it will call suspected outlier this point, okay. 1.5 of the size of the interquartile range, IQR, interquartile, above the first quartile or the third quartile, because if it is here, it will be nearer to the third quartile. If it is here, it will be nearer to the first quartile, okay? If it is vertical here, it will be above or below. So it will be on the left or right, or above or below. Here he is talking about above or below. Above the first quartile, okay, or below the third quartile. This is called 1.5 times IQR rules for outlines, okay? So 1.5 of the interquartile rule for outliers. I hope this one is clear. Sorry, the video was very lengthy, but I hope that this topic is fully digested and you fully understood it. Thank you very much.